Hello everyone, this is the solution video to quiz 2. Now we had a getPID function which accepts basically the transfer function, some overshoot value and a settling time value, and it gives us basically two transfer functions which we can then use to visualize all the PID controllers that satisfy the overshoot and settling time value. And of course we have a free parameter, which in this case was KP. So GES and GZS was basically a root locus transfer function in terms of KP, which we can then visually analyze and see which controller does the best for us. Here, of course, the idea is again a dominant pole placement. Now we are going to take some transfer function and we're going to return some transfer function objects. So everything inside getPID can be or will be the symbolic toolbox, but outside of getPID we will not even use that at all. So it's kind of a tool that gives you quick idea of a PID design problem. And possibly maybe PIPD, because you can neglect GZS and just look at GES to come up with a PIPD controller. So now here's an example code. When we provide the transfer function here, the overshoot value and the settling time, it will return us these two transfer functions. You can then use some root locus, rlocus plot commands to see what's really going on. So let's dive right into it. We have basically our first task is, as usual, define S, get the numerator, because we are basically embedding the TF to sim part here. Denominator. I'm not sure why MATLAB suggestion is not working, or it's somehow suggesting interesting stuff. So when we use the length, finally, and subtract 1, that would be our order here. We have ns equals 0 and ds equals 0, and then a for loop where I up to length then, and then ends. Now this part is quite standard, so I'm going to just do it here, times s to the power of n minus I, but then it could be negative, so add 1. So repeat this for ds with the denominator, and then our basically GSS should be complete. So I assume that this one is correct, so I'm going to move on. Now the classical PID design is going to be as follows: KP, KI, and KD. These are real values. We're going to have that basically. You can use GSS and FSS and then use that to end up with the characteristic polynomial. I'm just going to skip that part to remind you that there's a quicker way of calculating this for the classical exams. There's KD times S squared plus KP times S plus KI. So the numerators, numerator of the system, numerator of the controller, plus denominator of the system, denominator of the controller. That should give you the characteristic polynomial. Now, of course, we have also the zeta value here, which is minus log overshoot divided by the square root of pi squared plus log of overshoot squared. And then we have omega n, 4 divided by ts times zeta. That should give us basically that. Now, this part is still the obvious part, so the desired polynomial. But the issue is the following. Most of the time, our dependence in this code throughout this semester, you might have recognized that or picked up on that. Most of the time, the problem is about the residue polynomial, because we can use basically this. This is always a second order polynomial. We can use this n here to get rid of the order of the open loop system, and you can use this approach or TSS approach to end up with this exact point here. So up to this point, we have no issue at all about GS's order. But at this point, when we're going to define PES, we need to know the order. because we will subtract 2 of that and add 1. The reason behind that is the following. PID is order 1, n is the order of the open loop, but then again we place 2 of these, so there's an n minus 1 here that we need to get rid of. And if you somehow can generate a residual polynomial automatically, so this basically quiz is more about PES than the PID design. If you can do that, then you can just generalize this code and use this all over the place. So how can we come up with this or generate this PES here? So first of all, we know that we need n minus 1 as the order. And, well, in the PDF, as far as I remember, there's something, there's a clue here. Where was it? So here, you may check, so it is possible to create a residual polynomial for any order. You may check out the documentation of sim and subs. So that part is important because we've not used this much in throughout the lecture. Well, we have used sim and subs, but not that way. So if you look at the help here, maybe help is not even enough. Maybe the documentation itself needs to be there. So is this... Yeah, there we go. First of all, we have something like this. Most of the time we use sims and just do our stuff. But here we need to generate a vector in order to create basically our polynomial here. Now, what I'm basically trying to explain here and do is the following. I need to do something like this, s to the power of n minus 1. So we can already do this. And then s to the power of n, s to the power of n minus 2. And then dot, 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 s squared, maybe 1 dot less, so s squared, s, and then 1. If we can generate this, which is not that hard to do, and if we can generate another one, which goes basically e n minus 1, and then e n minus 2, and then e2, e1, and then e0 perhaps. If you multiply this, so this is a 1 by n, and this is then n by 1, so it should give us a scalar. So this is basically the dot product of 2 vectors. If you can do this, or you can somehow, you might come up with a different algorithm that results in the same result, but this was what I was thinking about. If I can do this, then I should be good to go. Now, let me just get rid of this. I know that it is n minus 1. So what I'm going to do is, first of all, I'm going to generate a 1's vector here. So 1 up to n. And then I'm going to multiply that with s. So I have a bunch of s's. So this is basically s, 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 s. And what we can do, and what most of you maybe don't use, maybe use, I don't know, is basically these dot operators. So you can use a for loop, that's okay, no problem there. Just go ahead and use for loop if you're not really comfortable with this. But if you are, you can just go ahead and use this operator here. So what does this operator do? By the way, I'm generating basically these powers here. n minus 1, subtract 1, up to 0. So s to the power of 0. So this is basically an element by element power. So let me demonstrate to you that. Sims s. So if I have this, and by the way, let's come up with an n value here. Let's say n is 3 for some reason. If we have n3, if we have this portion here, this creates me 3 s's. And if I take the power here, it doesn't work. Why? Because we need parentheses here. First multiply with s, and then you can see, so I should basically be placing this one here. So you can see that the vector itself here is just a usual vector, 2, 1, 0. And this is basically, if we use a dot power operator, if the sizes match, then the first one will become the first power, the second one the second power, and it still remains as a vector here, like this. So that's basically a portion that I want to do here. So let me leave that here. So that's one piece. So I have basically this part here ready. That's going to be multiplied with something else. So what we can do is we can basically assign a symbol and then ask MATLAB to create us this vector here. You can see there's something missing, and we can basically get over it. So yeah, it uses basically n-1, let's say -1, 1. It uses this basically. So E1, E2, or maybe in reverse maybe. So the algorithm is basically using these indices for this letter E. So it can generate E1, E2, up to En on its own. But what we are missing is basically E0 or E on its own. Well, therefore I can just add something to it. But there's also something interesting going on. When I define PES, I don't start with E something. I can just start with E s to the highest power, let's say n, and then E times s to the power of n-1 up to the constant term E. So basically, I'm going to just skip the highest power and use the remaining part to generate my polynomial here. So maybe I should code it, then show you what the result is in order to be more clear. So let's create an E vector, and this E vector is going to be basically sim and use the letter E, and it is going to be a n-1 by 1 vector here. So, and I'm just going to place in the highest order coefficient as 1. Then I have this portion here. This whole thing times E basically. So yeah, let's store this in PES. And PS equals PS times E. Should be basically it. So let's display PES. Let's run main. Let's see if we have messed up anything. So now you can see my input was, it had 7 coefficients, so it's a 6th order transfer function, +1 due to PID, 7th order, -2 PDS, so 5th order raised to polynomial. And you can see I'm talking about s to the power of 5 plus as to the power of 4 plus bs q plus cs squared plus ds plus e. So that would be the irreducible polynomial that I would have defined, but you can see MATLAB can do this too. Of course, it complains about not assigning stuff, but I'm going to get to that. So you can see this is basically the most troublesome piece in the quiz. Yeah. I'm sure that there are lots of other ways. First of all, you don't really have to do this elegantly. You can just use for loops. So that's one way. And second of all, the whole queue is all about this part here. So now I'm going to throw in some other stuff here, like PS. Once you have that, you can just use and assume. That's not really that important, but yeah, we can just throw in this assume real part. Now, let's actually try to come up with a problem here. So coefs, and then PCS, s comma all. Now, of course, what we can do is we can just normalize PCS no matter what in order to prevent some problems here. So pol equals this, and then pol equals pol divided by pol first coefficient, and then pol should be equal to coefs PDS times PES s comma all. And yeah, let's display basically the whole problem here. So as you can see, since we have normalized the polynomial, it's not a big deal to insert a 1 here. Basically, this coefficient should be the highest order term of pol, but if you normalize both sides, then it's basically not an issue at all. Now, how can we solve this? So first part was this whole thing here to generate PS automatically. But then there's also another issue where we need to basically provide the parameters that we want to solve and then just solve for them. And once we've done that, another issue will arise. So let's store the solution in sol. Let's provide the problem. And then what we're going to do is we need to provide KD and KI, but then the whole range of E coefficients that we want to solve. Now, since in E we also have the first term 1, what we can do is we can just give the whole E vector here, the second one up to end. So this should basically give us the solution that we are looking for. Yeah, the issue here is that E is basically a column vector. So I'm going to take the transpose, and there we go. That's the issue. You can see that we have all the parameters that are necessary, KD, KI, and then E1 up to E5. Because we had basically a sixth order system, seventh order closed loop, we have basically 7 equations, 1 trivial, making 8, but also 7 unknowns. So solving a PID problem for a given settling time and overshoot ends up being the same every time. And the reason for that is we're using basically two parameters, KD and KI, for example, to place 2 poles based on zeta and omega n. And we have a free parameter, so it means that we have a parametric solution. So yeah, we know what the solution looks like. And usually what we do in order to get basically GES and GZS is to substitute that. So we need 2 polynomials, basically, in order to create what we want. One of them is going to be PES. So we have PES, but what we want to do is we want to substitute into PES the solution here. Now at that point, it is quite nice to have this subs version. So maybe in the documentation, again, we need to look for subs. And there's something that is quite nice, and I don't know if it's showing up immediately. Let me see. There we go. The second paragraph here. Subs s comma values, where values is a struct, replaces the symbolic variables in s in the struct which are field names in values by the corresponding entries of the struct. So throughout the lectures, I don't use this because this is kind of a lazy approach. You have to know what you're doing before you do it. But here at this point on this week, it's quite not important anymore. It loses its importance. So what we can do, instead of doing sol.kd should be, or kd itself should be sol.kd, what we can do is we can just use the whole structure here, and it will replace all the corresponding field names in the symbolic variable with the values in that struct, in that field. So it's quite nice because it gives us directly what we want. So again, there we go. You can see that PS2 here has no other coefficient than KP because we can substitute everything into it. So we have a way of defining residue polynomials on its own or automatically. Then we also can solve them automatically, and we can substitute them automatically. You would maybe, at this point, you're maybe asking yourself why we didn't use this all along. Well, you have to earn it. You have to just go through that whole coding stuff in order to learn what's really going on here, because otherwise it's just going to be memorizing it. So that's not a good thing. But we should also be able to have some automatic tools. So this is one of them. So let me just place this somewhere here. So that would be a good point. There we go. So we also have PZS. So that is KDS square plus KP times S plus KI. And we can again repeat the same for this. PZS2 and then PZS. So PZS2, let's see what it's looking like. There we go. Now we can see again, we only have KP and a very long result here. So we can use VPA, of course. There we go. Now you can see we have basically a zero polynomial. We're not really interested in the residue coefficients if we are not looking for stability. If we would look for stability, then we would again use this vector here or this sol here, and then substitute that into the vector and use that resulting vector for the root table analysis or something else, some sort of a stability analysis tool. So that's also possible. So we can also come up with a stability tool here. So we have basically almost what we want. The only remaining thing here is the conversion from polynomial to transfer function. So 1 plus k times g s is our root locus equation. And if you look at it closer, you'll see that this is basically a fraction of ns divided by ds. When you multiply everything with ds, you will see it looks like this. So what we can do is we can take a polynomial that has only one parameter. We can separate the k terms and non-k terms. And the part with the k terms is basically the numerator, and the part without the k terms is basically the denominator. The fraction between these two will give you the transfer function. Then you can use that transfer function to plot the root locus. So that's basically what we're going to do. In order to do this in reverse, because we have already this polynomial and we're looking for the k terms and the non-k terms, what we're going to do is we're going to use the coefs here. So maybe let's call it temp, or maybe coef. Coefs. But instead of using s, we're not interested in the s terms, we're interested in the k terms here. Of course, it's this kp in our case. So we're interested in this. Here, coef1 is going to be the k terms, and coef2 will be the non-k terms. So therefore, we again will take some coefs. But this time I'm going to use S. So I'm looking for the S term here. So we have the k terms and the whole vector representing that polynomial, and then the non-k polynomial, non-k terms, and the coefficients of that polynomial. So the only thing that remains is basically converting them into a double, maybe, because our free parameters kp, we did get rid of the s terms because this is now not a polynomial, it's a vector. Now I can convert everything into double. If I fail at this point, there should be an error somewhere. But if not, then this is going to be the transfer function. So I'm going to call it GES because that's what it is called. You can see we have assigned GES. We're just going to repeat this whole thing for the zero polynomial here. Instead of using this, use this one here. Instead of defining GS, define GZS. There we go. We have basically our GES and GZS here. Now, in the documentation, I guess I have the same thing here. So 0.5 seems to be the same here. Now, the cool thing about this is, what we can do is, since we have this tool now, and we're not interested in anything else, so let me just suppress all the outputs here. So we've defined that, That's also okay. So this solution is not needed anymore. There we go. Now the nice thing about this is we can just use a figure and then maybe a subplot. Maybe not even. Hold on for this moment here. R locus GES, GZS, and then change the title to residue poles, and then zeros maybe. And if MATLAB decides to give the result, there we go. You can see now, we can see for the KP values what the movement is basically. Now, it seems like for our settling time and overshoot values, we will have two residue poles on the right half plane, even four of them. They start out like that, but then the two of them enter the stable region here. So therefore we have an unstable closed loop here for any positive KP. Immediately I can see that this is basically going on here. And yeah, the zeros are on the left half plane for most of the time. So yeah, what we can do is we can maybe increase the overshoot value now. And you can see it's still not really working out for us. Let's change basically the order of the system here. Let's drop down a little bit. Now you can see the order did drop. And you can see we've basically created a tool. Now, it is possible in MATLAB, we are not focusing that much on that, but it is possible to, for example, just squish in a text fields here for the numerator and denominator and a small button here, and then you can enter the data from the graphical user interface at this point, hit the button, and then have this plot react to it. Then you can just deploy that and you have a tool. Now, at this point, it is important to mention that we're more interested in using the symbolic capabilities of MATLAB and to get to know the whole theoretical stuff behind the scenes. Once you have completed that, once you have the whole package, you can just go ahead and create some nice tools that is aimed to do something. But most of the time, due to the separation rule of functions, I need to remind you that this isn't perfect. This is a perfect example of creating a tool, because everything inside is basically symbolic and does some stuff, but everything outside is compatible, or the inputs and outputs are compatible with the control system toolbox at this point, because most of the time users will want to use this using the control system toolbox. If you have a symbolic transfer function returned, it's not quite compatible because it's not a control system toolbox element. So this is why we have this get PID sort of thing here. Yeah, and once you have chosen that one, you can just go ahead and look for basically the PID here. Of course, we could also return multiple stuff here. For example, the parametric expressions of KD and KP, or KI and KD would make sense, but that's not the point of the quiz. But it would be nice to return them too as optional variables. If someone is interested in that exact PID, they should be able to pick it up. So, hope that this was helpful. See you in the next videos.